So here we can see in this slide a format of a redirection pointer. And now we'll see where we see it more. Here is the XML case. As we can see here, a pointer redirects the execution to the attacker's supplied code. And here we see it again in the VML case. A pointer, a virtual function pointer, redirects the execution to the attacker's supply code. Not only here, we see it also here in the keyframe exploit. Here we see it again in the ODB exploit. And the last one, exploit that was written with the Alexander library, and we see it again, it's depend in a pointer that will redirect the execution to the attacker's supplied shellcode.
We were concerned with, I mean, Moti works in Tel Aviv and I'm in San Diego, is, we're looking constantly at malicious data. We're constantly looking at all these exploits. And, we're not really looking at a protection mechanism that can go into the compiler or, it could be going into a product, but what we were concerned with is a detection mechanism that we could build into multiple machines and look for a commonality between heap spraying, Alexander's method for his heap lib library. And as we were looking through and kind of debugging all the exploits, the commonality between all of them was pretty simple. It was constantly, calling a virtual pointer and redirecting to the heap. It's a pretty simple concept, but we were like, well, let's play around with this and take it one step further and make a tool, where we can take something kind of generic and detect these types of exploits. So basically that's what we did. We took the tool, and what the tool does is hook all the calls that follow the following format. The following format being a call to a virtual pointer. And when that call is actually executed, we check to see if the execution is being redirected, either directly or indirectly, to the heap. So as we said, we called this little tool XMON, exploitation monitor. What we were looking for was something that was generic in exploitation techniques that we had seen so far. We tested it on, we deal with 80 to 90 million websites a day, and out of those, a huge magnitude of malicious websites. So we tested it on thousands of different exploits, and it was successful across all exploits. But we wanted to work not on only specific exploits, but any new vulnerability that might come out. We don't want to keep on changing it. We wanted something that had minimal configuration. So XMON is going to actually be deployed, internally across multiple machines. We wanted it to be something that was pretty easy and fit into our larger framework. We're talking today basically about heap corruption exploits, but XMON as well has other type of exploit detection techniques within it. It has stack exploit detection and heap exploit detection techniques. One thing that we found pretty interesting is, okay, so it's detecting, generically exploits, but we also sometimes, it would be nice to know if XMON could determine which vulnerability is actually being exploited. And what we found was that because that call to that virtual address it's not always the same, but in a lot of cases for vulnerabilities, the offset from the base DLL to that call is generally the same. We can figure out which vulnerability is actually being exploited. One nice thing too is we're also concerned if it's malicious or it's not malicious, but we'd also like to know if we had allowed it to execute, what would have happened. So we can dump the shellcode for offline analysis, or dump it into our automated machines that can kind of run it through, decode it if necessary, and figuring out what that exploit's attempting to do. The main concerns for XMON were speed and accuracy. So a little bit about the details of how XMON actually works. Right now, XMON is only injecting itself into Internet Explorer. XMON is a DLL we created. It's a module. And we're injecting ourselves into Internet Explorer. It could be across, it could be Firefox, it could be other browsers, but currently we're only using Internet Explorer. We've created some IDA plugins to basically go through all the DLLs, Internet Explorer, and generate a list of all the virtual calls. And when we start up IE with all the DLLs, we basically patch all those virtual calls. But we'd also like to patch DLLs that are getting dynamically loaded. The VML, for example, the VGX DLL doesn't get loaded. When IE starts, it's going to get loaded if it detects that there's VML code necessary in the JavaScript or in the HTML. So we also, patching is kind of an ongoing process. We do it dynamically as DLLs are being loaded. Just to give you an idea of the number of calls generally in some of these DLLs that we had to patch, the XML MS0661 vulnerability, which was an MS XML4 DLL, it had a total number of calls of around 2,000. Now, we wanted to try to be smart about which calls we actually patched. Which calls we were actually patching. We didn't want to patch 2,000 calls. Although this is a research tool, we still try to focus on speed and performance. And so what we would determine is, well, we don't need to patch all the calls. We needed to patch calls that came from objects that are dynamically allocated. They're allocated on a heap. So, if you have C object, C equals new C object, that's going to be allocated on a heap. If it has any virtual functions, those are the virtual functions we care about. So we wrote some more IDA plugins, and we did a little bit more kind of runtime analysis. And it's still kind of in the research phase, but it's dramatically less calls than 2,000 calls that we're actually hooking. So how can we tell if execution is being redirected to the heap? There's a few different methods that we were playing around with, but page permissions is generally one. The heap in the stack process memory has a basic characteristics and layout. We can tell if it's getting redirected to the code section, to the stack, to the heap. And if it's getting redirected to the heap or the stack, generally there's no legitimate reason why that should be happening. And so that's definitely a trigger for malicious behavior. Content at that location is also an indication that something malicious is happening. In heap spraying especially, the content on the heap is going to be something, similar to what Alexander showed before with a 0C, 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 or 05, 05, 05, 05. Generally, it's going to be some type of NOP instructions that are also a legitimate heap address. So those are the two types of things you'll generally find, when doing a heap spray. Now, it's just the reality that a lot of exploits aren't written correctly, they're poorly written, and they crash. A lot of proof of concept code is like this. So what we wanted to do was also catch these type of exploits. So what we decided to do was hook the structured exception handler by hooking KUser exception. And this allowed us to basically catch any exception that was happening. Sometimes these were, exploits, and sometimes this was just the browser crashing. And then we dump it to our kind of, our machines that do automated analysis of what might happen. We might offload it to an analyst who will look at it in a little bit greater detail, see if it was actually an exploit, a 0-day of some sort, or if it was actually a known vulnerability. So when we're looking at any type of thing that we might have written, we're also looking at, well, how can we get around it? And potential limitations is something that we're constantly working with. I mean, as I said, we kind of tested all the exploits that, constantly, about 1,000 different exploits in 1,000 different ways that weren't at all similar to each other. They obviously use the same vulnerabilities at times, but they might have different shellcodes, different methods, either using the heap spray method or using Alexander's method. And the types of times when XMON might not be the most useful is when trying to detect malicious websites that actually aren't hosting exploits. And when that is basically, phishing website or potentially damaging software. The user might visit the website and be prompted to download an exe, and the user happily agrees. Well, this happens all the time. XMON isn't used for this specific purpose. We have other types of systems in place, like sandboxes that are going to, be able to indicate that this is malicious behavior. Another issue that we found was if, for example, in the Yahoo ActiveX control, we visited a site with Xmon and it was hosting a Yahoo ActiveX control exploit. The machine that Xmon was on didn't have Yahoo ActiveX control installed. And so what actually happened was that it couldn't patch Yahoo ActiveX control and couldn't determine that the website was malicious. And playing around a little bit with exploits, what we determined as well is a lot of times you'll have the call that'll get redirected to the heap or call that'll trampoline to the heap. And one thing that we played around was a call that redirected to a set of instructions that flowed for a little bit and then eventually led to the heap. So Xmon tracks, some set of instructions that eventually jump to the heap, but there's a certain limit where it stops. The main point is that Xmon isn't the solution to all kind of exploit websites, but we have multiple other types of systems in place that are going to catch these types of malicious websites. So detection in its depth is definitely something that we want to stress. In the grand scheme of things, how does Xmon fit into our systems? So, to give you a little bit of insight of some of the technology that we have when we're scanning malicious websites, we have a multitude of different types of sandbox technologies. Generally visiting a website, allowing whatever behavior might happen, what might not happen to happen, and then figuring out how the state changed. We have reputation modules that basically look at what country is this malicious website hosted on, what are the links that are contained in the source, who owns the website, what hosting provider is it on, what are the relevant IP addresses that are around it, are they known to be malicious? Static detection modules, looking at signatures, and not only looking at exact signatures, but basically if that website might contain some type of polymorphic JavaScript, something like what Billy talked about today, decoding it and then matching against those signatures. Another type of modules, which basically where Xmon fits in, as well as it kind of fits in those three other types of areas. So the types of systems we're talking about is kind of low interaction systems and high interaction systems. Low interactions are basically signature scanners that obviously aren't just looking for exact signatures. They do some decoding of JavaScript or some obfuscation on the pages, then match signatures. But these type of low interaction kind of systems have to take a lot of upkeep. You have to constantly come up with a new signature. They're looking for known exploits, known proof of concept code, generic methods sometimes for signatures, but kind of takes a lot of constant upkeep. The high interaction systems are sandboxes, basically. They're relatively slow. You constantly have to restart the state of the machine, and they detect malicious activity based on unauthorized modifications. A little bit of detail on the high interaction. So generally you start with a fresh machine state. You launch one single browser. You visit one URL at a time, and you allow for state modifications to happen. And you can only visit one URL at a time because you are monitoring the entire state of the machine. You compare the original state to the modified state, and you determine if it's malicious.